and you can see if there's any difference between when I try to prepare and when I don't. Is the video on? Okay, or the audio stuff. Okay. Oh no, someone in the coat and tie, but not the lecturer. Okay. In any case, let's talk about a couple of things. I think I forgot to mention yesterday when I was talking about the ratio analysis diagrams. I mentioned something about grain size, but I think I forgot to say the only thing that gives you both strength and toughness is fine grain size. You can alloy steels, you can alloy aluminum alloys, and you can get better toughness, you can get lower toughness, you can get higher strength, but generally when you go to higher strength you get lower toughness. The only thing microstructurally or chemically, compositionally in a metal that gives you both strength and toughness is fine grain size. Okay, so people have tried to refine grains for years, and they actually have gotten down to such fine grain sizes that you have a hard time telling whether the material is got grains. Hi, Adam, you're here. Great. I was going to lecture if you weren't. Okay. So, good. You're going to use a laptop? Okay, it's right here. Just pop right in here. So Dr. Powell is an MIT grad. He was an undergrad and a graduate student at MIT. He later went off to NIST, National Institute of Standards and Technology. As a researcher, he came back here as an assistant professor, became an associate professor, and eventually left to work on this. Uday was your thesis advisor, wasn't he?
Became my advisor, yes.
Yeah, okay. Yeah. Adam had the problem of his thesis advisor dying, so don't any of you do that to your advisor. But anyway, but Professor Uday Paul, who had been here in chemical metallurgy, had developed a process which Adam will describe that can make virtually anything on the periodic table that's can form as an oxide, can make it in a pure way, clean way, and I'll leave it to that. Well, actually, let's see. Oh, it's because you haven't hit the thing to hopefully it will start working when you hit it. Is that? It could be something on the controls over here on the display, but I don't think so. Oh, okay. Okay. Anyway, Adam, actually, you got an undergraduate degree in both materials and economics, right? Yes. Okay. So I've asked him to speak to some of the externalities. I know he'd rather talk about the technology, but he's currently the chief technology officer of Infinium, which has got about $20 million worth of government funding to make magnesium. Oh, 10. Okay. They're applying for more. I told you yesterday about magnesium and the size of the market, and I told you some of the things actually that Adam might tell you, so I won't tell you again. Well, wait. I mentioned the problems in Detroit, and they need a stable supply of magnesium if they're going to incorporate it. So you can give more details on that. Actually, is it okay if we videotape you?
It's fine with me. Sure.
Okay, fine. Oh yeah, we have to switch. Yeah, you ought to have the mic.
Must be in a bad mood this morning. Excuse me.
So the schedule is I will lecture tomorrow. Dr. Belmar will be here on Monday and Tuesday. I think we might not have class on Wednesday. We'll check on what he's going to do on class. Well, we're getting close to the end so far as that goes.
Right. So while this is working its issues out, though, ask, are most of you in material science, or is there a variety?
About half mechanical engineering, 40% materials, and two ringers from nuclear engineering.
Okay, okay, terrific. Great. Let's see. So,
But they're interested in materials.
there we go.
It's not the old F7 key, is it?
Not on this machine. Okay. So hopefully we'll get out of vertical, and then we can do this. There we go. All right. So let's go this, that, change. Sorry, this never happens except situation like this. Okay, start. And view on.
There you go.
Yay, all right.
Something's happening.
Great. All right, so, terrific. When I was a student here in undergrad, a grad student, Tom was well known for having early morning classes. That was the only 8 a.m. class that I ever took, so it's not necessarily the best time for an undergraduate. This is. I will talk about some things that I find very exciting, and so hopefully that will keep you engaged and interested as well. That clean metal production for clean energy. Great. So most of the slides that I have are really about the technology of this company, Infinium, which I started 5 years ago with a colleague. So I'm was in material science, as Tom mentioned. My colleague's name is Steve Derazinski. He was in mechanical engineering. So that's between the two of us, that's most of the class, except for the nuclear engineers, though he did work in the nuclear industry. So I'll talk about clean metal production for clean energy. I'll talk a little bit about some of the issues around it, and begin by motivating the problem, talking about clean technology and dirty metals. So as you've probably heard, metal production is a relatively dirty process. Generally goes metal oxide plus coal to metal plus CO2 and everything else that comes along with coal. So that's sulfur and heavy metals and soot and all of that stuff. For renewable energy and energy efficiency, it's especially dirty, and I'll get into some particulars. So neodymium and dysprosium are very important for very high strength magnets that are used in high power to weight motors and generators. So that's most of the growth is in wind turbines where you need high power to weight because you're supporting this weight on a long steel tower, and so lightweight is important. Hybrid and electric vehicles as well, and power to weight is important. It's an interesting thing that the Tesla uses an induction motor, as you may know. It's just rare earth free, but is heavier and a little bit less efficient because you have to have a copper coil generate the magnet instead of permanent magnets. So as a result, you take a little bit of energy to run that magnet coil, and also add some extra weight. close to 100% of the rare earth metals in the world are made in China. It's about 95% of the rare earth elements, but the metal production generally happens in China for reasons I'll get to in a moment. So rare earth magnets are outstanding. You know, if you look at the technology changes in terms of magnet sizes required to generate a certain magnetic field, the interface. You know, neodymium iron boron is an amazing magnetic material. This is so just the volume required for a permanent magnetic field, and with it the mass has gone down quite a bit. However, you know, Chinese rare earth industry is notorious for a lot of pollution. So you Google images, you know, China rare earth pollution, and you find things like this. And then you find this. This is our competition. This is a Chinese neodymium plant. And basically they use very small cells. These are molten salt electrolysis cells. Have we talked about molten salt electrolysis?
I've mentioned Hall Perot, but I haven't really talked about the cells.
Okay, well, this is basically the Hall Perot cell. So I'll talk a little bit more about this in a minute. But the way it basically works is you have some kind of a bath with a molten salt, generally fluoride salt. And you add to that metal oxide. So in this case, neodymium oxide. In the aluminum case, it's aluminum oxide, etc. And you put into it you know, some kind of a cathode. In this case, they use tungsten. You can see the tungsten cathodes down the middle. And an anode. In this case, they actually use the entire graphite vessel, and they make a little bit of neodymium metal in the bottom, and then harvest that with, in this case, a molybdenum ladle. And the only anode technology that people can get to work with this is graphite. And carbon is a contaminant in neodymium. It reduces the magnetic performance. It's a diluent for the magnetic performance of the magnet. So you're making this in a graphite vessel with graphite anodes. You're going to get some carbon in it. So what they found is that workers can be trained to visually and by feel, try to figure out about how to minimize the carbon content, and then they ladle these out in 1 kilogram batches because the carbon content is very variable, and then they analyze each 1 kilogram batch and sort them for carbon. Extremely labor intensive, and that's why it's only done in China and somewhat in Vietnam. This is one of the reasons that Chinese production has come to dominate the world's rare earths, and there are other reasons as well, some market reasons. Actually, since Tom asked me to talk about this, I'll talk about it a little bit. Very famously, Deng Xiaoping is quoted to have said in 1982, Saudi Arabia has oil, China has rare earths. And China certainly has a very large rare earth supply, and in fact, for heavy rare earth metals, if you look at the bottom of the periodic table, everything basically to the right of samarium, China has by far the best deposits of the world in the world. Neodymium is a light rare earth. It's found all over the world, but dysprosium, which raises the Curie point of these magnets, is found pretty much only in China, except in tiny concentrations in other parts of the world. China has had exported with very low prices for a very long time, and made it very difficult for the rest of the world to produce, such that one of the best mines in the world in Southern California for light rare earths actually shut down in 2002. You can see due to Chinese competition. Then in 2010, anyone know what happened to the rare earth market then, or what some Chinese actions? Yes? They stopped selling to Japan, right, because of a border dispute. That's right. So suddenly there was panic throughout the world. Fortunately, Japan was well prepared because they had the analysis of the critical materials. Toru Okabe, who was a postdoc in Don Sadoway's lab years ago, he was a professor at the University of Tokyo. He kind of sounded the alarm well in advance, so that in 2006, when I visited his lab, he said, we're especially concerned about dysprosium. We also have a neodymium issue. And so they stockpiled a lot of it and had about 2-3 years worth of supply. So for the 2-month embargo, they were okay. Rare earth prices skyrocketed, a factor of 10, and they've since come down to about twice what they were before. But China is now imposing export restrictions, export quotas, and the suspicion is that they are going to have a lot of other projects are starting throughout the world, and that China at some point is going to drop prices again, have them go out of business, buy them up cheap, and then have even more control over the world's rare earth supply. But that's it's a suspicion or conspiracy theory. So anyway, moving on. Tom talked about magnesium for lightweight vehicles. It's the lowest density structural material, density of about 1.7 versus aluminum at 2.7. In stiffness-limited parts and applications, which is most of the car body, et cetera, a lot of different parts, you can save about 20 to 30% the weight versus aluminum, and cut the weight in half versus steel or steel and aluminum mixture. This is just shows a bunch of different parts made of magnesium by one particular die casting company in southern Canada. The largest of which is you can see on the left, the Lincoln, I think it's the MKT rear hatch door. And magnesium is expensive enough that in all of these applications there is some other secondary savings in the car. It's not worth it at current prices and fuel savings motivation, if you will, fuel prices. To substitute magnesium, except if there are other advantages. So, for example, in the liftgate application, the secondary savings is that with a lighter liftgate, you can use a smaller and cheaper motor. So it has other savings there. The most common one is the instrument panel beam that runs across the dashboard, holds all of the steering wheel, instruments, glove compartment, etc. And that is in steel about 30 different steel stampings spot welded together. Magnesium, it's one die casting, so it's a neat part that's somewhere in there. The Corvette engine cradle. Corvette is a sports car, so it's a little bit more weight sensitive. They've had a fiberglass body for a long time for that reason. But again, it's part consolidation. You can go from about 10 steel stampings to a single magnesium die casting. And I like talking about this because magnesium's problems have generally been in corrosion and creep. But here it is in a application right next to the engine and getting salt water thrown at it from the road. But it doesn't corrode. Engines aren't falling out of Corvettes since 2006. And it works quite well. So moving forward, there are projects involving the front end. The front end is important because it's kind of the hard part. It has to support the engine and crush and accident and all of that. And beyond that, the full vehicle and the advantages, some of them I mentioned. It's easier to die cast than aluminum because it has half the solidification shrinkage. It machines faster, dent resistance. It has this interesting elastic hysteresis, which I saw a lecture once and I understood it then, but about 5 minutes later I couldn't explain it to you if I tried. Just the physical metallurgy of how this elastic hysteresis works, but it ends up absorbing energy in the course of elastic deformation. So it has this very unique vibration damping. So you can achieve very high vehicle weight savings versus replacements of steel and aluminum. It's a key weight reduction strategy. Magnesium is produced by one company in the U.S. The Chinese competition shut down all other production in North America. And basically they've survived by two things. One is a wonderful connection to their congressional delegation that won them, among other things, a 111% tariff on Chinese magnesium, but also a Clean Air Act exemption, so that they've been called the nation's worst polluter. They're on the Superfund list. And Don Sadoway was actually involved in a lawsuit to try and shut them down. He was saying that you can see the green chlorine emissions, plumes. Back at the time, they didn't capture just about any of their chlorine. They just vented it. They have a ferric chloride tailing pond that is poorly enough protected so that when there's heavy rain every 10 years or so, some of it washes into the salt lake. And so So, major problem. So that's magnesium. It's done by chloride electrolysis in the U.S. In China, it's done by a more polluting process that I'll get to in a moment. Moving on to so silicothermic reduction, which, if you know your chemistry, using silicon to reduce magnesium oxide is backwards, right? Magnesium should reduce SiO2, but what happens is silicon has extremely low vapor pressure. Magnesium has very high vapor pressure. So if you put silicon and magnesium oxide in a vessel, pull a vacuum, you'll get a little bit of magnesium vapor pressure, heat one end, cool the other, and you get magnesium transport, and it condenses into solid in the other end. But it takes a lot of energy to drive this reaction. So I'll get back to that in a minute. It's a very, very long carbon payback time in terms of it takes 275,000 kilometers of driving before the fuel savings pays back all the carbon you put into producing it at the front end. So not really practical. Solar grade silicon. Let me skip this, and this we have some time for it later. So I co-founded Infinium 5 years ago with co-founder I mentioned, Steve Derazinski, mechanical engineering, class of 90. I was 92. We now have 22 employees in a 12,000 square foot facility out in Natick. As Tom mentioned, this is a metal extraction breakthrough invented and patented by Uday Pal. So it uses a zirconia solid electrolyte between the molten salts and the anode. And we'll talk about that in a minute. There's no carbon, no chlorine in the process, so there's zero direct emissions. Our tagline has been clean metal production for clean energy. Let me skip this for a moment. Basically, in a typical aluminum cell, the anode just sits in the molten salt, and you generate CO2 right there in the molten salt that you apply a potential, and so you produce liquid aluminum at the cathode. At the anode, the oxygen from the aluminum oxide reacts with the carbon. You produce CO2. But in addition, the alumina is not completely dry, and it picks up some moisture from the atmosphere. And when you have moisture at high temperature and fluoride salts, you make some HF. So what comes off in terms of water and HF is about 10 to 1 to 20 to 1 water to HF ratio, but nonetheless, it's enough HF that you really cannot build a heat exchanger that can withstand the kind of acid corrosion. So in its place, we put a zirconium oxide solid oxygen ion conductor between the molten salts and the anode. We use a liquid metal anode. You can use the cathode materials of solid oxide fuel cells, porous perovskites, but it's very complicated. Liquid metals are very simple and robust. So you can use liquid silver to make pure oxygen, or you can pipe in natural gas to create a reducing environment, and then you make some CO2 and some water. It's about the same energy content per mole of oxygen you pull as graphite. So it's pretty much equivalent to a graphite anode energetically, except you make half the CO2 because it's CH4. And you don't have to make the graphite anode, so you save all of the energy and CO2 emissions involved in graphite anode production, which is a very messy process in the aluminum industry. And furthermore, natural gas is cheap these days, right? As you all know. So this has a lot of advantages. It eliminates something called the anode effect, where if you get CO2 bubbles forming along this, you get very high current density at the anode, and in that case, you don't just have oxygen reacting with the graphite oxide ions, but fluoride ions, and you form perfluorocarbons. So CF4 has about 6,500 times the global warming potential of CO2. C2F6 is about 9,000 times the global warming potential. So this eliminates that because you don't have any fluorine in contact with the anode. The zirconia is very selective. It only allows oxygen through. So Eliminates HF in the anode gas because, again, you don't have the anode is separate. It's sort of in a separate chamber from the rest of this. Eliminates the graphite anode plant. As I mentioned a moment ago, you can capture the energy from this CO2 and water, or from this oxygen, where you really can't from the anode gas in a Hall cell plant because of the HF. Furthermore, the only way to contain this liquid cryolite is in solid cryolite in the traditional Hall cell. In our cell, because you've separated out the anode gas, you have a reducing environment in here, and so there's no CO2, there's no oxygen, and we can contain this in a metal. We can use steel, in fact, just cheap welded steel vessels. And for that reason, we can insulate around it and have very low energy losses. If you contain a liquid in its own solid, it takes a lot of cooling to maintain that solid. Imagine trying to have a long-term glass of water made out of ice, right? If you're heating the water, you have to cool the ice. It's very inefficient. It also cuts the cell footprint, because now instead of a flat anode and a flat cathode, you can go into the third dimensions. You can have these zirconia tubes extending deep into the molten salt and the cathodes as well. And there's some limit to that. We can get between 3 and 10 times the productivity per unit cross-section area versus the Hall cell. So your overall footprint of the plant can be about half, we think, of the footprint of a traditional aluminum plant. Furthermore, as I mentioned, you can produce an oxygen byproduct or use natural gas fuel, steel vessel, and this also enables direct electrolysis of magnesium oxide. Magnesium oxide electrolysis has been a goal of the industry for a very long time, since Charles Hall in the U.S. and Hérault in France showed that it's possible for aluminum oxide. I've been trying to do this, and this is because for both aluminum and magnesium, it's very expensive and very difficult to make anhydrous, high-purity chloride material. That you have to do it either by carbochlorination, where you take magnesium oxide plus chlorine in the presence of carbon. It produces CO2 and MgCl2. It also produces dioxins and furans, right? Carbon, oxygen, chlorine. Or you can you can add hydrochloric acid, and then you have magnesium chloride solution, and then you can dehydrate that. But that's very difficult to do. It's a lot more difficult than it sounds, because you have to manipulate the pressure in order to avoid hydrochloric acid evaporation from your cell. It's the most capital-intensive operation in production of magnesium. So for this, the magnesium Hall cell has never worked. It's complicated why. Carbothermic reduction doesn't work. Silicothermic reduction leads to very high energy use, as I mentioned. So this is why magnesium chloride is very expensive. Yeah, trust me, read up on it if you're interested. Okay, so this is so our technology for magnesium is similar to what I just mentioned for aluminum, except that magnesium boils at 1090 Celsius, and this is right in the heart of the zirconia's high conductivity temperature range. So for that reason, we can run it above 1100 and make magnesium vapor. And that's really neat, because whereas the Hall cell for aluminum has to have very high purity aluminum oxide, any impurities go straight into the product, we can take 98% pure magnesium oxide and make 99.9% pure magnesium through this sort of inline distillation, basically. So it's not only aluminum oxide electrolysis, but it's not only magnesium oxide electrolysis, but it's high purity magnesium from moderate purity magnesium oxide. We get very high current, energy efficiency. So the main issue is the zirconia tubes. This idea has been around since the late 60s. And in fact, if you look up in the patent literature, you see Swiss Aluminum has a couple of patents that were granted in the early 70s on basically this technology because of all these advantages that I mentioned. However, if your zirconia tube doesn't last very long, then your tube costs basically outweigh the advantages. So Uday Pal's real breakthrough was a combination of chemical metallurgy thinking and some stubborn persistence that finally found molten salt combinations that don't destroy the zirconia. And I can talk about it because he's at BU, he's published this. Turns out magnesium fluoride, calcium fluoride eutectic, unlike cryolite, does not attack the zirconia such that we've seen in 500-hour tests, you get about 100 microns of zirconia corrosion. So if we run for 5,000 hours as our target lifetime, that's a little more than 6 months, 1 millimeter of corrosion. And if they last for that long, then the costs of zirconia tubes per pound or per kilogram of magnesium ends up being very low, a small fraction of our total cost. So that's the enabling breakthrough here. And if you're interested, I can talk about why that is. But okay, so this is something like how it look in industry. You have your crucible producing this. You continuously feed the magnesium oxide in, produce oxygen at the zirconia tubes, and then we use argon to both stir the molten salt and dilute the magnesium, because again, if you know your electrochemistry series, magnesium plus zirconium oxide becomes zirconium plus magnesium oxide. But if you dilute magnesium to an activity of 1/10 or lower, so 0.1 atmospheres or below, 0.16 atmospheres, but anyway, then it's thermodynamically stable. There's no reaction. So we dilute it to about 10%, and then condense liquid magnesium in the condenser. We circulate the argon. We get over 99.9% argon recovery. So so we use very little argon, and then just tap that out. And this illustrates one other advantage. We produce liquid magnesium, and because we have no emissions. A nice thing about this process is that it scales down well, that there's no emissions, there's no treatment of the hydrofluoric acid containing anode gases. The only emissions are basically either oxygen, which is, as Sadoway likes to say, you're even allowed to emit oxygen in New Jersey. Sorry if there are any New Jersey residents here. But also, or if you use natural gas, then it's natural gas combustion products, which are, MIT emits a lot of that, right? So as a result, you don't have to have a lot of expensive equipment to contain that. You don't have to apply for any EPA permits, which is often the most the biggest time delay. You're getting ready to build a plant. You apply for the permit, and you wait. Your plant's all ready, but you have to wait another year, because all the federal, state, and local permits take that long to come in. Well, if you don't have emissions, then you don't have to get permits. So suddenly, instead of having to build 60,000 ton or 200,000 ton plants, you can just build small 2,000 ton or 5,000 ton plants. You can build them right next to the consumers, so right next to a die casting plant or a continuous strip. What do you call it? Strip casting. Twin roll strip casting, that's what I'm looking for, to make sheet, and just sell the hot liquid metal, and that cuts your customer's energy cost in half, because they don't have to heat and melt the material, just contain it, put it into their machines, and use it. So you can charge a premium, and it's a nice side benefit to the economics of scaling down this process. In terms of other externalities, energy use and emissions, Pigeon is the name of the professor in Canada who invented this silicothermic process for magnesium, and that takes a huge amount of energy. As I mentioned, 100 kilowatt hours per kilogram. So what the Chinese do is they put their magnesium plant next to a coal mine, and then the energy is almost free. So coal energy is a lot cheaper than electrical energy. This Western electrolytic is U.S. Magnesium, a company called Dead Sea Magnesium in Israel. I think they're still in production. But sorry, that's the old name of the company, Most. I haven't updated this slide. It used to be called Metal Oxygen Separation Technologies. And this is a third-party energy and emissions model showing that we use about twice, about half the energy and have somewhat less CO2 emissions. I should mention also, oh yeah, they actually emit some chlorine. This is all per kilogram of magnesium production. This assumes that we're using magnesium carbonate as our raw material, and so that's CO2 is 44 versus 24. That's about 2 kilograms of CO2 for every kilogram of magnesium right there. So take that away, and this goes to something like 3 kilograms instead. So quite a bit less energy and carbon dioxide. Compared to aluminum, aluminum primary production is about 24 kilowatt hours per kilogram and 12 kilograms of CO2 per kilogram of metal. So this is our kind of design concept. So you see that the crucible with all the tubes in the top left, condenser and tank for the metal. We have a 2-stage condenser. Actually, an intern from the Material Science Department helped to invent it a few years ago. So he's on our patent application, which is about to be granted. But anyway, Tom is also an inventor there. Argon recycling, and I didn't mention this, but because of impurities in the molten salt, you have to continuously remove some of the molten salt. So it's about a 6-month residence time in the cell there. So this is about 40 ton per year cell concept, and fits into a relatively small box. We put it in a box with the heating inside to have an inert atmosphere, so we can just use steel without having to use very expensive stainless steels. So I'll get into our early production prototypes. This is an old picture. It's running now. So just in terms of what happens to the impurities, the basic reaction is magnesium oxide to magnesium plus oxygen. But the feedstock has a lot of impurities, and particularly more electronegative metals like aluminum, iron, silicon, or rather they're oxides. Those plate out on the steel cathodes, so that we put the cathodes in as for every metric ton of magnesium we produce, we get about 5 kilograms of these impurities plating out on the cathodes. So we have to replace those every so often. We think we can sell, or if not sell them to the steel industry, then they'll just take them because aluminum and silicon are good at reducing porosity of ingot castings, large steel and ingot castings. Okay. Zinc and sodium are the only impurities that, if they're present in the raw material, will get in, because they're both very high vapor pressure and also their oxides are a little bit less stable than magnesium, which is counterintuitive. You think of sodium as being extremely reactive metal, but actually in the oxide series, it's a little bit less stable than magnesium oxide. So chlorides just evaporate at these temperatures very slowly to the point where we end up with a steady state where it's built up in the crucible enough so that it's evaporating off at the same rate you're feeding it in. That gets into the condenser. We actually haven't seen it in the condenser yet because we haven't run for long enough, I guess. But so about 5 kilograms, it will separate out, just density separate in the condenser for every metric ton of aluminum. Sulfates are present in the raw material. That's our only emission in the course of heating the raw material. You get 100 to 200 grams of SO2 emission per ton of magnesium. So this is low enough that we should not need any permits. This is the issue: the calcium and sodium. That those will accumulate. Potassium. Those will accumulate if we do nothing and just cause. Eventually cause a fine precipitate which messes things up. And for that reason, we just add some magnesium fluoride. Some of it forms magnesium oxide and calcium fluoride. Right? It's all just ion soup in the molten salt. And magnesium oxide, we just make magnesium and oxygen with that. But then we also form this calcium fluoride, magnesium fluoride salt in situ. So we just kind of, by adding the magnesium fluoride, we just kind of accumulate more salt, and it about doubles in volume every 6 months, which is why we have to drain it. So, all right. So, as I mentioned, high purity magnesium from low purity magnesium oxide. So let me pause for a moment and ask if there are any questions on magnesium, on the economics, externalities. I've talked a little bit about them and about less pollution and different things. There's no real incentive for reducing CO2 in the United States, though the incentive for reducing other pollutants through this permitting process is a big one. Any other questions on this trade or yes? Okay. No, there isn't. There are multiple producers of magnesium oxide and about 1 million tons per year of production capacity. In the last 10 years, about half of that has shut down. But there's lots of magnesium oxide supply. Sorry, one moment.
Remember, the magnesium production worldwide is only about 250,000 tons.
Right.
So if you've got 1 million tons of magnesium oxide, you'll be okay for a while.
Here we go. So so it's produced in Michigan from magnesium chloride in salt brines, in Nevada from magnesite, that's that magnesium carbonate. In seawater, actually this is an old slide, the seawater production in Florida has shut down, but there's still a company in Delaware and a company in California that profitably produce magnesium oxide from seawater, which is neat. It's about 0.15% of seawater. Well, sorry, getting ahead of myself. Canada, in particular British Columbia, has some of the best deposits. There's a new mine in Ontario with a 1 million ton per year production of magnesite and talc. British Columbia and Liaoning, China, have the world's best resources. In Liaoning, they're much better developed. 1 billion tons of proven reserves ready to be taken out of the ground. And British Columbia, it's 3 billion tons of inferred resources. So we think somewhere in there is about 3 billion tons. So it's not quite a apples comparison. But the biggest source by far is the oceans. So 2 quadrillion tons of magnesium, which, if you do the math, if you do the entire body and white of a car in magnesium and a bunch of other components, and say about 1 ton of magnesium per vehicle, that's enough for 300,000 cars for every person on Earth, right? So even if you use 0.1% of it, that's still a lot of magnesium. It's basically a limitless resource. So, all right, other question? You have another hand? Yes. Yeah. No? Okay. Oh, sure, go ahead. Yes, it does. And yeah, we do. The supply. Zirconia is not such a big issue. We use yttria stabilized zirconia, and yttria is a big issue. Now we, when actually the powder cost is the biggest component of the cost of the zirconia tubes, and it's made from something called zircon sand, which is a relatively high zirconia concentrate in sand, but then you have to concentrate that further. But we're only going to run our tubes till they're about 1/3 corroded. So then we have a nice, very high concentrate zirconia source for about 2/3 of our powder materials. We think that step is down the road after we've solved a bunch of other problems. When we scale up, then we could place a significant amount of demand on the world zirconia market, and not such a large fraction of the yttria market, because it's used for lots of other things like fluorescent bulbs and kinds of other things. So yeah, that is a potential issue down the road.
However, why can't you use calcium or magnesia stabilized?
Well, we are working on that as well. The issue there is that they have about half the ionic conductivity of yttria stabilized zirconia. So this is where we've. Okay, so It's very difficult to get powders of calcium and magnesium stabilized zirconia that are fully stabilized and of high enough quality to make the tubes that last as long as we want them to. So we're actually, as part of our DOE project, we are making our own powders. And we've made a couple of tubes. They don't. We're still working on that right now. So yeah, that's eventually the cost model will make that decision for us. Is the savings in yttria in the tubes and the savings in the yttrium fluoride that we have to put in the molten salt so that it doesn't leach out of the tubes, is that worth? Well, balance of that versus the higher energy, and furthermore, if you have half the conductivity and you try to pump the same current through it, you get a lot more joule heating and thermal stresses. Zirconia is terrible for thermal stresses. It has very low thermal conductivity and thermal expansion, 12 parts per million per degree, comparable to a lot of metals. So that's. That, as I mentioned, the cost model will make that decision for us once we've done that. We have some other ways of improving the zirconia lifetime and performance, which we'll be able to talk about in a couple years or so. so other questions?
So what do you think you can get a price point if everything's successful compared to aluminum? Right now, magnesium is twice the price of aluminum.
Yeah, it's about $2 and a quarter per pound. It fluctuates versus aluminum at $1. What I can say now is we think we will be very competitive on the world markets, which without the U.S. tariff, it's about $1.40 a pound, and at that price, you're sort of density equivalent to aluminum. So you can put magnesium into the same die casting volume as aluminum and pay the same amount for the metal. Now it's not quite fair because aluminum is a little bit stronger and higher modulus, and so you can't quite do that. If you're stiffness limited, you can do 20 to 40% less material less weight in magnesium than aluminum. So not quite the density ratio. 40% if you're just a plate that you're trying to optimize, 20% for other geometries. If you're strength limited, you can do about 10% better in magnesium than aluminum. A little better than that in plate bending, and not as well in pure tension, etc. About pretty comparable to aluminum in pure tension. So there's no real weight savings in a pure tension application. You have to use more volume of magnesium. Anyway, you get the idea. So our original cost models showed us a little bit better than the world price of magnesium. Based on what we've learned experimentally now, our new cost models are showing a lot lower, and I'm viewing that right now as some slack, so that all of the unexpected costs in running a magnesium plant that we don't know because we haven't run a plant will make up some of that. That's about what I can say now on videotape. Sorry, showing my age on video. Yeah. So okay. Other questions?
Well, it's about time for me to let it go at 9:20 anyway.
Oh, okay. Okay. All right. Well, great.
Sure. Thank you, Adam.
All right. Thank you.
Okay, I'll be here tomorrow to finish up my portion. Simone will start finishing up his stuff on Monday. Thank you.
All right. Come on. There we go. Oops. What is this? Oh, thank you.